So what is EnergyPLAN? EnergyPLAN was developed by Aalborg University in Denmark with the idea in mind to help a developer or an energy systems analyst in the transition from like a fossil fuel based energy system to a sustainable renewable energy system. And it was also one of the first tools which tried to integrate different energy sectors with each other, electricity and heating, and also transport. Because the vision was already then in the late 90s when they developed the tool that, of course, when we invest into wind, it will lead, and it has led into overcapacities. Wind, the electricity prices drop. For example, we can use electricity now much more for heating than we used it before in some countries. Yeah? Of course, we have Sweden and Norway, which are exceptions because we have so much hydropower. We use electricity for heating since 50 years back. So electricity from the overcapacities which we create can be used in district heating systems with heat pumps and accumulator tanks. Large storage tanks are built and hybridized, let's say with biomass or solar thermal. But also it opens also the possibility with electric vehicles, because we need, of course, when we replace fossil fuels in the transport sector with electric vehicles, we create electricity demand. And the vehicles have storage, so that will also help to balance an integrated system. And electric vehicles, I think already today the prices have dropped, as with other technologies we have experienced, solar PV, wind onshore, wind offshore, the prices have just come down in the last 10-15 years tremendously, and even electric vehicles will come down even further. But I think already today, if you are a commuter and travel every day, you're 15, 20, 50 miles back and forth to your workplace, already today I think it would be worth to invest into an electric vehicle. At least in Sweden it's worth it when you compare the prices of fuel and electricity and what electric vehicles cost today. And they have less service costs, etc., etc. So EnergyPLAN includes the components electricity, heating, transport. Transport has also a lot of features where it can convert electricity into what they call synthetic fuels, hydrogen, methanization, etc., etc., and can then be used in the transport sector. But I think for us here and in this training, we won't look at the transport part. It's just a bit too much. Electricity and heating, we look at these two parts. So the energy demand is modeled in the different tabs. This is the demand part with electricity, heating, etc. And in the like reference energy system picture, it's this orange boxes when you open. They are not clickable, it's just an overview about what EnergyPLAN provides if you have installed and opened it. And then of course the supply side here. We have hydro, we have other renewables, solar, wind, and onshore and offshore, etc. And then a lot of conversion options in between. Supply. And then what is perhaps of interest in some of our cases, as we discussed, electricity storage and also heat storage could be an option. Heat storage in the case if you have district heating systems. Many like older district heating systems have not installed larger storage tanks. But today with like this, as I said, the overcapacities of wind, the cheap electricity prices can be used to charge the storage and then used in peak demand periods. Many people think district heating utilities earn the most when it's the coldest, but the problem is then during that period they actually have to start their peak boiler. Usually they have 2 or 3 boilers, and the peak boiler is then often fired with fossil fuels, not with the large boiler which carries the base load, is perhaps wood chips, biomass, and then the peak boiler is still fossil fuel, and that is actually costly. Costs also in Sweden CO2 tax, but people don't pay more during peak periods. There is also a trend now in district heating that to introduce time of use tariffs, that people pay more when it's very cold, so that there is actually an incentive in the market to invest into creating more energy efficient buildings. Okay, it supports scenario developments. And how does it do that? Of course, you create your model, put in all the data, and it's not so that you can have, like, on one half you have your base case and then you enter new data in a second half. You will use your base case and change data there and save it in a separate file and also document what you are doing. So that's a little bit a challenge to keep track on what you are changing, because you can change your model easily with a few steps and then you save it and you have, let's say, overwritten your base case. So that needs to be kept in mind when you have built your reference case. Save it and copy it, and then you start creating a scenario in a copy of the original. So that's a little bit small hint how to use it. So we can run these simulations. They are very fast. They take just a second or 2 seconds in the system when we enter new data. And most of the tools which look on long-term optimization or simulation, they run in 1 year time slices only. Yeah? And then you get results for 2020, 2030, 2050, etc., etc. EnergyPLAN was modeled to or developed to have 1 hour time slices for 1 year. So 8,760. It is a special case in EnergyPLAN because they actually model a leap year, so you need to have 8,784. Yes. Yeah, so that's a little bit special. When you get data for certain years, then you always have to extend this extra day. Yeah. But the advantage of this 1 hour time slices is that you actually, when you include renewable energy sources which go up and down every hour or even every minute, which we cannot model with this tool, but every hour at least we can have higher or lower wind production, and also higher or lower demand in our households or on the weekends or on the peak hours during the evening, etc. So this can be covered by this model, and those tools which help to develop long-term strategies, they do not cover this. Yeah. So what do we get for results? We get, of course, the energy balances, demand and supply, and then see how it's balancing out. And as we invest in local wind production, we can see easily, okay, we import less, and also then we look at the costs, because importing costs money and exporting creates revenues. So we will look at this as well. It has some pre-designed reports which we get when we click the run buttons, run screen or run clipboard. They produce the same results, but with the run clipboard you can easily paste it into for example, Excel. Most of us have Excel. Run screen just puts the results in a separate window, and then you can look quickly at it. And then we have this run print option, which creates a 2-page report, a predefined report with the key data, which can be perhaps attached in an annex to a report which you would create. And with this run clipboard, you can copy it into Excel and then create your own beautiful diagrams and comparing scenarios, etc. And just looking at this picture, we have the navigation in this tree navigation part, but we can also switch on this tabulator navigation. Then we have tabs up here, which will also allow us to click into the different screens. But I think for my experiences, it's most practical to use the navigation tree, but you will find out yourself. So just to summarize, developed by Aalborg University in Denmark from the 1990s, as I said, to support the transition to fully integrated and renewable-based energy systems and covering all energy sectors. I think that was also important. Otherwise, you cannot really talk about integrated if you don't have a model which helps you to work on that integration. And then it's a simulation tool. It's not an optimization tool. Simulation on an hourly base for a 1 year period. Then I usually get the question, okay, how do we then model 2020 or 2030 scenarios in that time? This is just, for example, you look at your population development, your economic development. You see, okay, your population growth in the the trend for population growth is like 2 or 3% per year or 1%. Then you see instead of 2,000 households, you will have 2,200 households by 2025 or 2030. And then the household energy consumption then has to be created and enlarged by household energy consumption per household, and then you increase, and then you have a scenario for 2030. Same with economic growth, when you know that you have a quite big industry in your peninsula, and that you could discuss with the different industries and say, okay, we plan to expand, and this is what we expect in the next 10 years, and then you can create the 2030 scenario for energy consumption. At the same time, you should consider more efficient use of energy. So on the one side, energy demand is increasing, but it's also dropping because we invest in energy efficiency as well. And then other cases for scenarios, 2030, for example. Okay, today there is no wind farm in our community, but the master plan, which we just create, foresees that we will have, let's say, 40 to 60 megawatt in our community, and that can be then implemented in a 2030 scenario. So you can, even if you have only 1 year period in a simulation tool, you can design your future scenario as you go along, like putting the right input data into the system. So this is, for example, how the graphics, when you open the output navigation here and click on the graphics, you will have some diagrams like this: electricity demand for the year, the electricity production for the year with different sources, and then this is the electricity balance for the grid. So in this case, we have most of the time we have import from the grid, and only in a few hours per year we have export from the hydropower or the wind power which is installed. So, and this, you have the buttons of clipboard, so you can actually copy paste these diagrams into your reports as well. If you don't like them, you export the hourly data. Whenever you do a run, you actually get monthly averages in this predefined reports. When you want to look at the hourly data, you switch on the hourly possibility here. Then you get long reports, but they can be used then to create this diagrams on your own, and you can build on that. So EnergyPLAN has been used in the past on municipal level, on national level. It was created actually for national level, and the first examples are of course Denmark, because it was developed in Denmark. And then it was also used on a wider level, like it was used for this European heat roadmap. I had a small slide in one of the presentations. So it can be used also in a wider perspective. Again, it integrates heat, electricity, industry and transport sectors. And we have seen many academic publications on how to use it and in which cases it was used. A very interesting one just was published a few weeks ago, I think, about the Åland Islands. You know, these islands which lie in the Baltic Sea between Sweden and Finland. They have two power cables, one from Finland and one from Sweden, and they want to, of course, expand their tourism industry, etc., and the power cables are insufficient. So they either have to invest into expanding the power cables or make sure that the investments into local production and do not only include production but also storage and balancing, and to make sure that the power cables which they currently have are not overloaded, both in import and exporting when they invest into wind, for example. So that was a very, very well done. I can perhaps also share it. It has a supplementary materials which also describes very well how to create your input data, etc.
That would be very relevant to.
So how does the workflow look like? We already started the workflow. We have created these reference energy systems. Some of you have already done some inventory on the number of buildings, etc. When we know now how much energy each of the buildings consume in average, then we can create like the annual energy consumption, annual demand. And this is what EnergyPLAN needs most, the annual aggregated data on energy consumption on the different sector. And as a second part, this hourly distribution profiles, perhaps you have come across when you have downloaded and looked at it. So we need to know how this annually produced or generated energy is distributed over the year. So these two are the main data input which we need. And those data, of course, are very site specific for the country or for Athlon or for any of the examples we have seen before. And so the annual demands or supplies and the hourly distribution data. So the hourly distribution profile, like if a household would use like 20,000 kilowatt hours per year, then you don't know yet how much is the peak demand on Friday evening. Yeah? So household electricity demand is usually you have a peak in the morning and a peak in the evening when the people prepare breakfast, cook in the evening or have the showers and the hot water boiler kicks in immediately. A commercial building usually has a peak over the day when all the people work in the offices. You have ACs running, the lights, the computers, etc. So this is the daily profile, and that can be sliced into hourly slices. Okay. And also all over the year, of course. We don't need these profiles for each house. We have, for example, for the heating demand, we take temperature profiles from the meteorological what is it called? Institution? Yes. Yeah, from MET. Yeah, in Sweden it's SMHI. You get hourly temperature data for the location or for the nearest weather station, and that can be converted then into the heating degree day distribution profile, which is actually the driver for then distributing the annual heating demand of 20 megawatt hours into like the hour time slices. Okay. Yeah. As I said, the aggregated data on like the national statistical databases are usually on municipal level. And everything below is more or less a bottom-up estimation. Yeah? You have like 200 residential buildings. You know, most of them are built before 1990. Some of them are built and then you have to like create your own estimation. As long as you somehow can justify your assumptions. Yeah? Of course, you will never get it exactly on the point, but if you are in the range of plus minus 10%, it's good enough. Yeah? When you remember the slide from the building regulations, yeah? From 200 kilowatt hours per square meter per year to 50. Yeah. So if you have a 150 square meter building for a residential home, which is, I don't know, the standard size, or is it smaller or bigger, then you can calculate the annual usage. Yeah? So our experiences, even if you go out and measure data, we have done some academic studies and student projects, and if you look at in one apartment building, 100 apartments, each and every flat has a different consumption, and it can range from between plus minus 50% from the average, because you have older people, you have younger people, you have bigger families, smaller families. Some are conscious about the energy consumption. And it's also very often in apartment buildings you don't have your own meter. Yeah, you get billed on average use of the whole building. So you don't really have in Sweden at least, you don't have an incentive at all to save. Yeah, yeah. So when your apartment is in the middle, like on top, on left and right, and below everybody is heating nicely, and you switch off all your heaters because everybody's heating, but you don't save any money because, yeah. So at least in our case, I don't know if in Ireland, if you have an apartment building, you have own meters for heat and water and electricity.
We would never agree to that.
Yeah. So averaging is taking away the incentive for saving, of course. Yeah. But if you have that, that's good. Yeah. Then everybody living in that building is actually having an incentive to save. Yeah. Okay, so that's like preparing data input, and then we feed it into EnergyPLAN. This we will look at later, how to use the different screens. And then we get, after we have done the input data, we get some results, and then we compare it with reality. Every model, of course, is a simplification, so we will not get an exact picture of the reality, but when we validate our reference, our case, it should actually like do what's happening in reality. And if you have deviations, It could depend on your assumptions, or you don't know the exact data of the technologies used, like the district heating system, the size of the boilers, etc. But you can always justify that, okay, we are within a certain range and we think our model is good enough for our purposes. Yeah? As we discussed also, starting with low-hanging fruits and etc. And then like resources, what land is available? Do we have like an area of like 2, 3 or 4 soccer field size which we can use for solar PV or not? Is there an old landfill which cannot be converted into building area because it's a landfill, so there we put our solar panels? Or do we have an old industrial area which is contaminated, which will also be very costly to like put it into a shape so that it can be used for human purposes? Put solar panels there, something like that. So you always have this, especially in the smaller community area, which like helps you to limit your scenarios. Okay, we're talking about scenarios. As I said, after you have done your runs and you know what data you want to look at, is it mainly carbon emission reductions you want to look at, or is it increasing the renewable energy share, etc., in the heating sector or in the electricity supply? And then you create your scenarios, and the scenarios again will lead to new input data, and then you do the simulation again, you analyze your results, and this circle will be done a few times until you settle down what scenario you really think is the best one. One of the case studies we did is the PTO case. And this report on the PTO case is quite comprehensive. It includes more or less a step-by-step guide on how to create one. But what was our starting point? The starting point was actually the climate and the energy plan from PTO, which is a town of about 40,000 inhabitants, or a municipality. The main town has only 20,000, and then we have the smaller villages around. And they are also a member of the Covenant of Mayors, and for that they have created this climate and energy plan, Sustainable Energy Action Plan it's called. So what were their ideas by 2020 and then also later by 2030? The idea was to replace direct electric heating with individual heating with heat pumps. So a lot of houses in Sweden have direct electric heating because of the traditionally cheap electricity prices. Electricity prices are going up, and the direct electric heating causes a lot of or high electricity peak demand during the winter period. And when, for example, another scenario says, okay, they want to invest in electric vehicles, then the electricity grid will not be able to provide the power for both the electric heating and the electric vehicles. So something needs to be done. Heat pumps is a scenario. And then a scenario example is because one of the goals in PTO is to become a net exporter of electricity. They don't want to import, but at least over the year balance, they want to be exporters. So one option for that is to increase wind power. They already have about 145 megawatt installed by today. And in the master plan, there is about 1.2 gigawatt, 1.8 gigawatt, I think, to install in the community. It's a huge community. So, and with energy plan, for example, you start off with this. This is the situation in 2015. It was at that time 58 megawatt wind. And when they want to balance like the net zero, with energy plan, you can easily find out, okay, where is actually the point where you reach this net export import balance. Then the electricity balance over the year looks like this, and they would need to invest into, or allow the municipality itself does not invest, but at least in the master plan they would need to, let's say, make space for 300 megawatt wind by 2020 to make sure that they reach their own goals which they define in their climate and energy plan. So that's just a very simple example to how energy plan could be used and to show okay, how the electricity balance will evolve. Yeah. And then the results, some more graphs here from what the energy plan itself provides. This is a copy of this two-page report. And then this is how results could look like as you implement or export your results into Excel. Like increased wind power increases, of course, electricity production within the community. Or primary energy demand, fossil fuels will drop in this case. Or CO2 emissions will drop because when you invest in wind power, you, in this case, reduce your imports, and imports have a carbon factor attached, like each imported megawatt hour has like 0.1 kilograms of CO2. Reducing import from the national grid reduces the carbon footprint of the municipality. I don't know if you have like in your municipality like a strategic plan to reduce the carbon footprint of the community. If you have policies like that, then like with EnergyPLAN, you can easily show how any investment in wind or in electric vehicles could reduce your carbon emission. Yeah. So I think we are way over time, but starting to get a little bit tired here. Not only me, I guess, also you around here. The idea was actually to get at least going to see if everybody has installed it, but I think everybody has done it. You have installed EnergyPLAN, you have get it to run, you have looked at it, clicked a little bit around, perhaps. Have you had a chance to look at the exercises as well? Yeah? No. Okay, there's a lot of training material also on the website, and the step-by-step guides for simple exercises. They provide the, let's say, the task, like in the school. You get your task, and you also, in the school, you don't get the solution. But then on the EnergyPLAN website, you also get the solution. Yeah? So it helps you actually to develop your skills step by step. But we will do some of it together tomorrow. I think it's really enough for today. We know where to get it, and when you have installed it and unzipped, oops, wrong button again. You will have a folder structure like this. You have the executable, which you just run, and then you have these directories which are mainly used by EnergyPLAN, and especially the data directory includes then the cost database, and then the data, which is the actual project data file, and then these hourly distributions, which we will see much more about it tomorrow. And in these distribution files, I managed with help of Xavier and of Christoph to create these hourly distribution profiles, which we need for all our projects. We have this HD data, the heating degree data, which are the converted temperature data. The temperature data file is also there, but we don't use it directly. Then we have, I have created and used this PV-GIS simulation or solar simulation tool, which is available online, which is provided by the European Union, the GRC, the Joint Research Center. So we have 2 solar files. And then we have the demand hourly profile of the national grid. So this is what we will use for the profile, the electricity consumption profile for our little case. Yeah? Of course, it can deviate a lot from our little case, but this is what we have got for now. Yeah? There is also the electricity prices here from S&P, or what's it called?
System marginal prices.
Yeah. Okay. We have also wind production from Ireland, which is the total Ireland wind production hourly profile here. It's of course a mix of offshore and onshore. So
yeah, it's onshore.
yeah, it's only.
There's very little offshore.
Okay.